Okay, good morning, and we're gonna go ahead and get started here. Anybody have any questions on anything? Okay, then let's go ahead and jump right into it. And we're going to go back. We're still looking at bones, so let's take a look here. Let me get back. We're just about I'm going to start here. Close enough. So, okay, let's. We're talking about bone structure. We're talking about the anatomy of the bone and the structure that makes it up. Remember, we're talking about living tissue. And our bones are covered by a membrane called periosteum. And this membrane has two layers. It has an outer layer made up of what are called Sharpie's fibers. And then it has an inner layer where we find the osteogenic cells. The osteogenic cells are the stem cells that we derive all of our other cells from. And that lines the outside of our bone. Now, on the inside of our bone, well, the inside cavity, because we have compact bone on the outside and spongy bone on the inside, and there's usually a cavity called the medullary cavity in the middle, and we will see the endosteum lines the inside of the compact bone. It also lines all of the spongy bone, it lines all of the cavities. Now here's what the periosteum looks like. This is the periosteum right here. The outer layer is made up of Sharpie's fibers. It's the outer layer holds blood vessels and nerves that go into and out of the bone. That happens all the time. We have lots of foramen in our bones so that these blood vessels can go in. Bones are not, as we know from looking at the skull, for example, bones are not solid. There are lots of openings in the bone. And all of our bones have openings to allow blood vessels, passage of blood vessels and nerves to go in and out. We call those openings a nutrient foramen. And it penetrates so that it penetrates here and then is in contact with all these clusters of bones and bone cells throughout. Now that layer is held, that artery, that vein, and that nerve is held in place thanks to what are called the Sharpie's fibers here. It looks like Velcro the way it's stuck to the bone. Now in the medullary cavity, it's either going to be yellow marrow or it's going to be red marrow. Now the yellow marrow is mostly fat. In adults, most of the medullary cavities are going to be filled with fat. There are a few places where it's filled with red bone marrow where we produce blood cells. When we're children, it's just the opposite. Most of the cavities, most of the medullary cavities and the areas around the spongy bone are filled with red marrow to keep making red cells for us, or making all blood cells for us. Now the endosteum, the inner layer, we have the periosteum on the outside, we have the endosteum on the inside. It also covers all the trabeculae of the spongy bone. It will cover it will line all of the openings through the bone where blood vessels and nerves penetrate. And it will also contain these osteogenic cells, these stem cells that will give rise to other osteogenic cells. That's what stem cells do. Stem cells, when they undergo mitosis, will always make copies of themselves first. Then then usually half of those stem cells become osteoblasts, the bone builders that lay down the matrix, the osteoclasts, the bone destroyers that dissolve the bone, and become osteocytes. Now, as I said, the red bone marrow is in the some of the medullary cavities. It is found in the cavities of the spongy bone around the trabeculae, and it's found in the diploid structures in the flat bones. The diploid, remember the diploid is a sandwich. Compact bone, spongy bone, compact bone. It's a bone sandwich, if you will. We call it diploid. And many of the diploid structures, bone structures, are filled with red marrow. The spongy bone in the middle is filled with red marrow. We find it in our sternum. We find it in the ribs. Those are all flat bones. We find it in the bones of the skull. We find that arrangement around the heads of the femur and the humerus, and we find it around the iliac crest, the top of the ilium. This is where we see hematopoiesis, blood cell production taking place. And this is, as adults, this is about the only place we have left, where we produce blood cells. When we were children, all the bone marrow was red marrow. Now it's just mostly confined to these few places. So we take great care to protect the blood producing cells. We don't expose them unnecessarily to ionizing radiation. If we're getting an X-ray, we may have shielding placed over the sternum, or and also the gonad producing cells too. You don't want to damage those, but you want to avoid damaging, exposing the blood producing cells or blood producing marrow, blood producing cells, to any type of ionizing radiation, because it would destroy them. I mean, this is one of the consequences of radiation sickness. Someone exposed to high levels of ionizing radiation, like beta particles and gamma rays, what happens is those cells are destroyed and can't produce blood. Can't produce the blood cells. It doesn't. When you're exposed, a person exposed to ionizing radiation in high levels is not radioactive, but they will have suffered damage, and the blood producing cells in the marrow are particularly susceptible. Okay, so here's our bone marrow. Again, this is the yellow marrow in the medullary cavity of a femur. We see here at the head of the medullary cavity, ahead of the femur, we have red marrow, in and around the trabeculae, because underneath the outer shell of compact bone, the whole head and neck region of a healthy femur are filled with spongy bones. Looks like it does down here at the distal end. Also, we have lots of spongy bone here. Spongy bone is great for flexibility and for strength without a lot of weight. So, we store energy with the yellow marrow. We produce blood cells with the red marrow. The red marrow makes all 7 different types of blood cells: the 5 white cells, the red cells, and the platelets. So this is a close-up of the head of a femur, and we can see, obviously this is the outer part of the bone here, but this is all spongy bone, and we see the red marrow throughout the surrounding all the trabeculae of the spongy bone. This is compact bone out here on the outside, and there's some yellow marrow in the middle here, but this is where we see a great deal of red cell, of blood cell. I keep wanting to say red cell, but blood cell production. Now, granted, we probably make more red cells than any other type of cell, but that's, this is what the red marrow area looks like. So what do we produce from the cells? So let me back up here. So you've just seen where the stem cells for blood production are, because it's one, the thing about blood cell production, there is one stem cell that will give you all 7 other types of blood cells, all 7 blood cells. You'll have one stem cell. It's called a hemocytoblast. You'll learn all about that in AP2. But this hemocytoblast is the stem cell. And then when it undergoes mitosis, it differentiates based on demand and need. It'll produce red cells, or it will produce any of the 5 different types of white cells. It will produce the platelets, and it will also make copies of itself. That's what stem cells do. Stem cells, their primary mission is to make sure that they stay there, because a stem cell can differentiate into a variety of other cells. That's what stem cells have the ability to become other types of cells within their cell line. So a stem cell that produces blood will differentiate the daughter cells into red blood cells, white cells, or platelets. The same thing holds true here in bone. Our stem cells are the osteogenic cells. Now, genic means, it refers to creation. So creation of bone, osteo is bone. So osteogenic cells are the creation of bone cells. So that's the stem cell. When the osteogenic cell undergoes mitosis, and they divide, bone cells have no restrictions about mitosis or cell division. They're not like muscle cells, they're not like nerve cells, but the stem cells will undergo mitosis and usually produce daughter cells that are identical. Obviously we know how mitosis works. We have the cell that's undergoing mitosis produces identical daughter cells. Now, usually what happens with a stem cell is that about half of those stem cells, the daughter cells, stay there as stem cells, and the other half will differentiate into a variety of other cells in the cell line. So, for example, the osteogenic cell undergoes mitosis. Half the cells stay as osteogenic cells so they can continue producing this variety of other cells. The other half, the daughter cells, are already predetermined to become osteoblasts or osteoclasts or osteocytes. So we get 4 different cells from the osteogenic cells. We get osteogenic cells themselves, because you can't take an osteogenic cell, can't take a bone stem cell and have it become an osteoblast without replacing the stem cell. So you have to make a copy of the stem cell. You have to make daughter cells so that you can use some of the daughter cells to become osteoblasts, osteocytes, and osteoclasts, and the other osteogenic cells remain. So osteocytes are the living cells embedded in the lacunae. They're not going to grow anymore, but they're alive. They're the organic component, or part of the organic component of bone. Bone's about 35 to 40% living tissue, and the other 60 to 65% is the hard calcium phosphate salt matrix. And these osteocytes, site means cell, so we say osteobone, so it's a bone cell. These osteocytes are going to be monitoring stresses and demands on the bone, monitoring concentrations of calcium and phosphorus, all this stuff, and they're going to trigger new bone growth, or they're going to trigger bone and more calcium deposition, or they're going to trigger bone breakdown. They're going to respond to the stresses that are placed in that bone. Because when bone gets stressed, when you're working, when your patient is engaged in some sort of physical activity, those bones are going to get stressed, and so the response is to get bigger and stronger. And it's the osteocytes that tell the bone that. they can monitor the twist and the turn and the pressure. Now, the cells that are going to start the process of building up more bone are the osteoblasts. The osteoblasts are the bone builders. Think of builder, think of the blast as builder. And the osteoblast will secrete the matrix. We call it the osteoid. It's soft and squishy, like a gel, and it has calcium and phosphorus salts embedded in it, along with collagen fibers. And the osteoblasts will build themselves in, will trap themselves in bubbles in here called lacunae, and they'll end up becoming osteo. The ones that are going to that build the matrix and get trapped inside the matrix are going to be osteocytes. The ones that don't get trapped and continue to build the matrix remain osteoblasts. And so we continue to lay down bone, and we develop into osteocytes as needed as we trap ourselves. You know, if you're an osteoblast and you trap yourself in a lacunae, then there you are, you're going to be an osteocyte. Then, of course, the osteogenic cells. And the last category is very, very important to us. These are the osteoclasts. The osteoclasts are the bone dissolving cells. They're large cells. They have a fringe edge here that allows them to almost slide across the surface of bone and dissolve it and release the calcium so we can use the calcium in other places. We need calcium for muscle contractions. We need calcium for nerve impulses. The heart in particular, we need the calcium for skeletal muscle contractions. We need calcium for cardiac muscle contractions. So we have very important needs and uses for calcium in our bodies. We need calcium for blood clotting. There's a lot of things that calcium is required for. And if our calcium levels are low, our blood calcium levels are low, we're going to get it from the bone. Plus, we use the osteoclast to remodel our bone. Our bone is constantly undergoing remodeling. We're shaping the bone all the time based on our activities, based on our needs. An individual who routinely works out and exercises, or works in a physically demanding position, maybe construction, for example, will see their bone mass increase, because there are more muscle. The muscles are going to get bigger. The muscle cells are going to enlarge, because the more you're exercising, the more you're putting demands on those muscle cells. They're going to get bigger. They're not going to reproduce, but they're going to get bigger. The bones have to respond, and the bones will lay down new cells, and the bones themselves will get bigger, and the bones will be shaped to provide the maximum amount of strength for the muscles to use when the muscles pull on the bones. So our bones will get bigger as our muscles do. And the osteoclasts are going to reshape the bone based on these demands. It's constantly altering the shape of our skeleton. In fact, they're responsible for breaking down bones so we can build a new skeleton, and we have a completely new skeleton in place every 10 years. And so this is the important role of the osteoclast. So, osteogenic cells, osteoblasts, osteoclasts, and osteocytes. One of the things about the osteoclast is they are very, very large cells, and they have lots of lysosomes present inside of it, because they're going to release those digestive enzymes in the lysosomes to dissolve the calcium, and so it can be captured. And then, of course, you have the osteocytes, the living bone cells. This is how big an osteoclast is. This is the brush border, the ruffled border edge of it as it's sliding across bone. Here, this is a tiny little or normal size osteocyte compared to the size of the osteoclast. There's our osteocyte in the lacunae, And here comes our osteoclast dissolving away that bone to release the calcium from the matrix. So it's a huge cell. It has lots of nuclei. So it tells us that during development, it was probably it's the result of formation of a number of cells that came together to produce this larger cell with lots of lysosomes in it. So that's part of the microscopic anatomy of our bone. When we look at bone itself, we see that it is organized. We look at bone, it just looks like a hard structure. But if you remember from AP1 in lab, when we looked at the different types of connective tissue, there was one slide that showed you compact bone. Compact bone looks like a circular arrangement. It looks like the cross section of a tree trunk, with the rings of a tree, but rings of trees and stuff like that. Well, that's what compact bone looks like in cross section. We call this lamellar bone because the rings of the bone that correspond to the rings of the tree, and you can't tell the age. You can't count the rings of lamella on a bone and say, oh, I know how old this person is. It'd be a pretty painful way of determining an age. But the lamellar bone, the rings are called lamellae. And as the bones get bigger, these lamellae, these rings, get added and increase in size. Now, if you are compact bone, you have three distinct structures here. You have something called osteons, and the osteon is a discrete collection of lamellae. You have canals running through the bones, and you have canaliculi running through the osteon, and you have lamellae that surround the entire bone itself and fill in all the spaces around the osteon. So let's take a look here. This is a bone, obviously. This is a long bone, and this is a compact bone here surrounding the medullary cavity, and we have blood vessels and nerves in there, and spongy bone on the edge of it. So this is what this little section looks like from here out. The long bones are going to have these osteons. Osteons are columns a column of bone that will run the length of the bone. It's like a tube or a pillar. Each one of these osteons runs the full length of our bone. When we have compact bone, for example, on the femur, the osteons that make up the compact bone run the full length up and down. So some of these osteons can be 24 inches in length or more. Each one of these columns is surrounded by other columns. So you have hundreds and hundreds of these columns arrayed in a circle around the center of the bone. And within each column, you have layers. Now, this column is called the osteon itself. This is the osteon. There's a canal in the middle called the central canal or the haversian canal that contains blood vessels and nerves. Now, these blood vessels and nerves are coming in from the through the nutrient foramen way out here at the edge of the bone, and then the artery and vein and the nerves will branch so that each artery and vein will end up in the central canal, the haversian canal of each osteon. And then from there, the nutrients are spread out to all the living cells. Now, the living bone cells are contained in these dark spots here, the lacunae, and we have canals that allow the blood vessels to migrate through the bone. We have the central canal or Haversian canal here, and we have little tiny canals called canaliculi. And those are these little lines that you see here. So in this osteon, you see a ring of bone and another ring of bone and another ring of bone, and you see these little lines running through here. Those little lines are tiny canals that connect each lacunae to another lacunae. So every lacunae in an osteon can communicate with any other lacunae, because the osteocytes are in the lacunae itself. So there's a lacunae, there's another lacunae, and within each lacunae we have an osteocyte. Now you'll notice these dark lines here within the canal. Those are extensions of the cytoplasm of each bone cell. This bone cell has extended its cytoplasm, its cell membrane, out to here, and this one has extended out to here, and where they join, there are gap junctions. So this bone cell can talk to this bone cell, and it can talk to this bone cell, and it can talk to this bone cell, and this one can talk to that one, and this one can talk to this one. And so everybody, all of the living bone cells, can communicate to each other through these cytoplasmic extensions of their membrane and the gap junctions through all these canals. So all these cells in each lamellae, each ring, can communicate with all the other cells in the ring and with other lamellae up and down and across. So these cells are all interconnected. We have a similar arrangement in the spongy bone. We look over here in the trabeculae, we still see lacunae with osteocytes contained within. We have the little canals in there, and they're communicating with all the other bone cells in there too. And they're going to monitor stress and torsion and twist and pressure, and they're going to respond to that. They're going to say, hey, we need to have more growth here because we have more demands being placed on us. And this person is right-handed, so we need to have a stronger bone in this area, because this person is, we are doing more with our right hand because, we have a right hand dominance. So the right arm becomes more powerful. So all these cells are communicating one to another, telling each other what's going on here. And they're all being supplied with nutrients from we can pass nutrients to each other. We can collect waste products from each other and eventually send it over here to the central canal of each osteon. Imagine if you just took a handful of straws. You go to McDonald's and you're getting a straw, and I guess they still have counter service. So you get a handful, but you decide you don't want one straw, you want a lot of straws. So you take out a handful of straws, and you're holding 20 or 30 straws in your hand. Now they're all the same size, they're all the same length. That would be that's what an osteon, what osteons look like. Osteons in compact bone are like straws that run the length of the bone. They're all the same size, they're all the same shape, and they're going to be clustered together. Now they don't make a perfect circle; they have an irregular shape. So we have to take into account for that. We have to put bone around the edge of all these osteons clustered together, and we have to fill in the spaces where they're clustered to give us the nice smooth appearance of our bone. This is the osteon. This is what an osteon looks like. It is the load-bearing structure in our bone. It has a central canal called the Haversian canal, where we have our blood vessels and our nerves penetrating. We have layers called lamellae. Every time we lay down a layer, the osteons are going to get bigger, and the lamellae form the rings. And now what's important about this is they're not growth rings per se, but they are load-bearing rings. Because as we lay down the matrix for these, for a new ring, we also wrap the matrix with collagen fibers. Now, collagen fibers are, collagen is the most abundant protein in the body. It's stronger than steel. You've heard me say that many times. Every lamellae is wrapped in collagen, but they run in opposite directions. So if one layer is spun to the right, the next one will be spun to the left as the fibers are laid down, and they run in opposite directions. By doing so, they dramatically increase their strength, particularly against twisting. By cross-hatching, by overlaying each layer of collagen fibers in an opposite direction, it makes them even stronger. And then we embed the calcium and phosphorus salts in the matrix among the layers. So you have a very, very powerful structure here that is load bearing, and it resists a lot of stress and twisting and torsion. It takes a lot to break a bone. It takes even more to try and break the bone by twisting it. And so, I said that we have the central canal, the haversian canal that goes through the center of each osteon. We have our blood vessels and our arteries and veins, or arterioles and venules, and our nerves are going to go through there. Then we have penetrating canals or perforating canals called Volkmann's canals that run perpendicular to the osteon, because that's that nutrient artery or artery and vein coming through the nutrient foramen on the outside of the bone, going in and going across, perpendicular to the central canal, coming in horizontally while the central canal goes up and down. So these canals take blood to the medullary cavity, to each individual central canal, to to the endosteum, if you will. So that the periosteum is supplied, the endosteum is supplied, the medullary cavity is supplied, and each central canal or haversian canal of every osteon. Okay, so I've said this already. The lacunae are the cavities that form around the osteoblast as it's laying down matrix and gets trapped in there. As the matrix is laid down, the osteoblasts also form these tiny canals, the canaliculi, that are going to connect every osteocyte to each other and to the central canal. And when the bone matrix forms and hardens, these canals stay open, and then the extensions of the membranes of the osteocytes come together with gap junctions. Remember, gap junctions are exactly what they are. There are gaps in the membrane that allow the passage of information, nutrients, ions, and stuff like that across the membrane very easily. And so we can send information from one cell to another. We can send nutrients from one cell to another. We can send waste products from one cell to another to ultimately get rid of them. But the cells are all in contact with each other. And of course, this is what it looks like. Here's a osteocyte. There's the canal, the canaliculi, and there are the extensions of the cytoplasm and cell membrane that extend out. And somewhere, further down the line here, we're going to see another cell membrane extended out there with the gap junctions. Now, as I said, imagine you've got those, a cluster of straws, and they're all the same size, and you're holding them together, but they don't make a nice, smooth surface. They're not held in place very well the way you're holding them, because there's gaps around the edges of each one, and it's not a nice, smooth finish. So we have to use two other types of lamellae. Now the lamellae, the rings work fine for the individual osteons, but what about the gaps? Well, we use what's known as interstitial lamellae. Interstitial is coming to be a term that we use when we're describing filling in the spaces, because we use interstitial cells, they're going to fill in the gaps around other structures. So we have interstitial lamellae. The lamellae, this interstitial lamellae, is probably leftover bone from remodeling, because our bones are always remodeling, and we're always tearing down osteons and making new osteons. So if we're tearing down an osteon, the part that isn't torn apart completely, the section that isn't torn apart completely, usually becomes the interstitial lamellae to fill in the gaps. We also lay down a circular layer called the circumferential lamellae that goes all the way around. And this round layer here is the circumferential lamellae. It goes all the way around the bone. These are the interstitial lamellae in here. And one of the things the circumferential lamellae does is it's another way to protect our bone from being twisted, because it's still, it's still filled with matrix with collagen fibers embedded in there too, and it still has living cells in there just like the osteons do. So while the osteons are load-bearing and strength and protection and twisting and torsion, so are these out here in the circumferential lamellae. So, and here's an example of what these interstitial lamellae look like. They're just, they're probably remnants of old osteons that have been dissolved, incompletely dissolved, that are left behind, and we use them to fill in the spaces around, in between the newer osteons. So, because remember, everything changes. Everything is in a state of change here. We are going to lay down a completely new skeleton every 10 years. So what you're seeing now won't be around in 10 years if you're looking at your bone. It will be replaced with something stronger and better. Now, so that's compact bone. Does a great job for us. Very strong, very powerful. We use it to resist twisting. We use it as load bearing. It's a great source of calcium. But we also have the spongy bone. The spongy bone is sort of peculiar looking. I mean, it looks like a sponge or a honeycomb structure. You saw what it looked like, with the trabeculae going every which way. And here, it didn't look like there was any. It's not bone for someone who's OCD. People, if you want your bone to be organized, you look at compact bone. If you want to look at bone that doesn't appear to be organized, you look at spongy bone. But the spongy bone has these trabeculae structures here. They're like beams and girders to strengthen the area where the spongy bone is located. Spongy bone is actually very, very strong. Spongy bone has the ability to take stress or a force and spread it out, to dissipate it. So that when we twist our bone, for example, at the hip, when we move our leg and the head of the femur articulates in the acetabulum, and shock is coming up our leg from running, walking, climbing, swimming, biking, whatever. Shock is coming up our leg and it gets to the head of the femur and it hits that spongy bone, and the spongy bone spreads that shock, that force, that blow, that movement. It spreads it out among all the bone that's there within the head of the femur. And what is transferred through the acetabulum to the ilium, and then to the sacrum, and then to the vertebral column and into the intervertebral disc is much less than what you dealt with initially. Now, we don't think of walking as creating shock, but it does. And that shock is transferred up our legs. Now, we don't notice it because it doesn't hurt. At least walking shouldn't hurt, but it may. The shock is passed up our legs into the head of the femur, into the acetabulum, and ultimately up our spinal column. And the intervertebral disc are going to absorb that shock. So is the pubic symphysis. But the original shock was dissipated by the spongy bone at the head of the femur, the spongy bone that was present at the end of the femur, near the tibia, and it spreads it out. That's what spongy bone does. It's sort of, imagine, if you've ever thrown a rock into a puddle or into a lake or a pond, and the rock hits the water and you get all these ripples that spread out. And the ripples right where you threw the rock in are very powerful. They're big. They're very strong, and they're very pronounced. But as the ripples spread out, they get bigger and bigger, but they're much less powerful. So if you throw this big rock into a pond, you get a big splash, and you get a great big ripple that comes out, and it spreads out and spreads out and spreads out. It gets weaker and weaker and weaker. And this is what spongy bone does. The trabeculae are lightweight structures, but they will take force. They will take a shock and spread it out. And so spongy bone is extraordinarily strong. And the reason that the arrangement of spongy bone looks irregular is because it's responding to all the stresses that are formed as we are, depending on our activity levels. And so these trabeculae grow every which way so that we can take shock and spread it out. Because what hits our spinal column is nowhere near what it was when it came up the leg. And it's thanks to the spongy bone. Plus, spongy bone, this is a good picture of spongy bone here. Spongy bone resists the forces. It can respond to stress in multiple directions. Consider the femur. The femur has force applied to it from all different directions as we run, walk, stand, sit, move around, engage in all of our activities. And the head of the femur responds to that very nicely. The spongy bone absorbs all these shocks. So does the head of the humerus. I mean, consider the range of motion that we have in the humerus. Consider what the rotator cuff muscles give us. Well, if you haven't had lab yet, you'll hear about those today. But consider the effect of the spongy bone in the head of the humerus so that we have this tremendous range of motion. Spongy bone gives us the ability to deal with stresses from all different directions and respond to them. Now, this is what spongy bone looks like, whether it's in diploe like this, or it is surrounding the head of the femur, for example. All of these trabeculae are going to take force and spread it out. And so we lessen the impact of actions on our bone by spreading the force out. And it's nowhere, the more we spread it out, the weaker the force becomes. So we can deal with motion in different directions. We can play contact sports and not become broken in various ways. If you played any kind of contact sports at all, or even sports that weren't supposed to be contact sports, and you fractured something, it's because you overstressed the bone. It's not like you did it deliberately, but you overstressed the bone, and the bone protected you as much as it could, and then finally the forces applied to the bone overwhelmed the protection of the bone itself. Okay. Now, part of this, and the great strength of our bone, we'll move into the chemical makeup of our bone. Great strength of our bone is not only the arrangement like of the trabeculae here and the osteons and the columns, but what makes up the bone proper, and that is a mix of organic and inorganic components. The organic components are the living tissues, the osteogenic cells, the osteoblasts, the osteocytes, what we call the bone lining cells that actually line the endosteum and line the cavities and line the canals, the osteoclasts, and of course the matrix itself, because the matrix is filled with collagen fibers and other organic material. The osteoid is what's secreted by the osteoblast. And when it gets filled with calcium and phosphorus salts and collagen fibers, it becomes extraordinarily strong. So the organic makeup of our bone, about 35% of its composition, 35% of bone is living tissue, or organic tissue, if you will. So now one of the great things that we see in our bone is that the collagen fibers, in addition to giving us great strength, also protect us from sudden forces. Collagen fibers also have the ability to experience or to use sacrificial bonds. Collagen fibers will actually break apart when a force is applied to them. That, you know, when a collagen fiber is exposed to a force stronger than it can resist, it will break apart. Now, you know, collagen is extraordinarily strong. It's, you know, we have lots of collagen and it's very powerful, but the collagen fibers will break apart when they get overwhelmed. Now, how does this help us? Well, collagen, by doing so, the collagen fibers absorb that force. And when they break, they are dissipating that energy. When the collagen fiber snaps, when it finally snaps, it is dissipating the energy that was applied to it. So the energy is being used is stressing that collagen fiber to the point of breakage, and the fiber breaks, and then the stress is gone. And that protects the bone. The collagen fibers will sacrifice themselves. They will break apart so that the bone doesn't break. Because, you know, it takes a lot of force to break a bone. I mean, if you've had a fracture, you know that, you know, usually, you know that you can't remember the actual event that fractured it. You don't remember the point of fracture. You just know, you remember the consequences of the fracture. You know, when you can't move your hand, you can't move your leg right, or something like that, or there's a lot of pain, but nobody ever remembers the actual point of the fracture. Unless, of course, you hear like a cracking sound, and some people do hear their bones crack. But to get to that point, you've got to overwhelm the collagen fibers and the strength of the bone. Now, the collagen fibers are going to sacrifice themselves to dissipate as much energy as possible. That usually works because, you know, we do things all the time that, forces are applied to our bones all the time that may damage the bones if the collagen fibers weren't there. But we're not aware of it because our bones don't break. It's only on the rare occasion that we do have a fracture that we've overwhelmed the collagen fibers. We've overwhelmed the inherent strength of the matrix of calcium and phosphorus in the osteons. So, and the beauty though of these collagen fibers is, yes, they will sacrifice themselves to dissipate the force. They'll break the bonds between them will break, and then they'll reform. So, you know, if you have a patient that fell down a flight of stairs and they're sore and they're bruised, but they have no fractures, One of, part of the pain they're experiencing is probably from all the sacrificial breaking of their collagen fibers. It takes a lot of effort to fracture a bone. It really does. So as long as the bone is healthy, it takes a lot of effort to fracture a bone. We see the neck of the femur breaking all the time in elderly people, particularly elderly females, as I'd like to say, your elderly postmenopausal female. We see the neck of the femur breaking all the time because osteoporosis has dissolved away the spongy bone underneath the thin outer layer of compact bone. So the protection and the strength is gone. It's just waiting to break. Okay. Now, the inorganic portion, mostly calcium and phosphorus salts. 65% of our bone is inorganic, non-living. And the calcium phosphate crystals are wrapped around the collagen that's embedded in the bone. That's what makes the bone hard and gives it, combined with the collagen, the hardness of the bone from the minerals give our bone its great strength. Bone does not compress easily. Bone doesn't twist easily. Bone is durable. Bones will last for hundreds of years after our death. As they say here, bone is half as strong as steel in resisting compression, being force applied to it that's compressing against the bone. So it's very strong. And it's as strong as steel in resisting tension, twisting, and turning. So it takes a lot to cause a fracture. The makeup of our bone, though, tells us an awful lot about an individual. And we encounter, we encounter skeletons all the time. We don't go out and say, oh, there's a skeleton. Well, this time of the year we probably do. But when you have archaeologists digging in certain areas, they find cemeteries that they weren't encountering, or construction. Construction workers building houses or something can come upon an unmarked cemetery. It's fairly routine to find the graves of soldiers from the Civil War in Tennessee. This is, it's as I say, an archaeological discovery, but we're going back 175 years, and the bones are still there. The soft tissue is long gone, but the bones are still there, and the bones can tell you an awful lot about an individual. Bones, in forensic science, but you find a skeleton, you discover a skeleton, and the bones can tell you an awful lot about that individual. I mean, obviously, first of all, you may get a good idea on age and sex. Well, obviously on the sex, because of the shape of the pelvis, they're going to give that away. You can determine their height by the length of the bones. There's a formula that lets you calculate the height, the body height, based on the length of the femur. You can tell a lot about the diet of the individual, because the mineral composition in the bones isn't going to change. You can tell what they did. The bones are going to assume certain shapes based on their occupation, because if you have a certain activity, some sort of repetitive action, you're going to see bones strengthen on one side or another. And of course, you can often tell the cause of death, especially if it is not a natural cause. If you look for markings on the bones from penetration of material like knives or bullets or blunt force trauma, all this is going to tell you a lot about the individual. You can tell if a person's been poisoned by certain types of poisons. Arsenic. Some people apparently people like to use arsenic as a poison, but arsenic shows up, stays in bone for hundreds of years. You can discover that. by analyzing bone, and it's not unusual to, if a body is exhumed after several hundred years, if the person was poisoned, it can be established by analyzing the bone. So it doesn't happen too often that it's dug up, but it can happen, and the evidence is there. More frequently, though, a body can be exhumed, in a questionable death, and analysis of the bone will tell you, hey, look, there's something here that shouldn't be there, or other, exposure to other contaminants like lead, for example, will stay in bone. So our bones can tell us an awful lot of things about an individual. Not just, oh, those are the names of the bones, but we can tell a lot more here. So anyway, moving on. We lay down our bone starting 6 weeks after conception. Now, at the 6th week after conception, we've been, fertilization and conception occurs inside the fallopian tube in an area called the ampulla. And then the fertilized egg, the conceptus, the baby, which is one cell in size at that point, is going to start growing immediately. We start out as one cell on the day of fertilization, and by the time we reach the uterus 7 days later, we're about 160 cells, and we're very organized as to what we're going to become. In fact, 2 weeks later, at the end of the 3rd week after conception, we have a heart and a heartbeat. The heart's beating after about 3 weeks. So at that point, we're about the size of a grain of rice, if you will, at the end of 3 weeks. But at the end, and at that point, we also start laying down a skeleton. We start laying down our skeleton made out of hyaline cartilage. So at the end of 6 weeks after conception, we have a complete skeleton in place, mostly hyaline cartilage, and a few bones are present, or a few structures that are going to become bones that are shaped like bones are membranes. The bones of the skull are in place as membranes. Everything else is hyaline cartilage. So we have a complete skeleton in place 6 weeks after conception. We're an inch long. We're all of our structures are in place and are growing. We at 6 weeks after conception, we have our fingers and toes and hands and feet and arms and legs and ribs and everything else, and they're growing. But right now, at 6 weeks, it's all soft tissue. It's all cartilage. That is the model that we use to ossify from. Ossification is the process where we convert hyaline cartilage and membranes into full-blown bone. Ossification is osteogenesis. Starts at about the 6th week and continues for the next 23 years, because we don't fully form our skeleton until we're about 23 years of age. We reach our adult stature finally at about 23, somewhere between 20 and 24. So 23 seems like it has been a number a lot of sources say. And after we reach our final adult stature, our skeleton is complete, then we start remodeling and repairing it, and that will continue the rest of our lives. So, but everything starts, the bony skeleton starts forming after the 6th week. We've only been in the uterus for 5 weeks. As conception takes place in the fallopian tube. It takes us a week to get into the uterus, and then when we're in the uterus, we're going to grow there. And so 5 weeks after implantation, we have a complete skeleton, and we're ready to start ossifying it. So there's 2 terms we use to describe this. what we say is endochondral ossification. The cartilage is referred to as endochondrium. So, or we call the cartilage, the bones that are present, that are made out of cartilage, are the endochondral bones. You know, we're going to call them bones. They're not bones in the sense they're filled with calcium, but they're still bones in the shapes of things that we, in the right shape. So the bones are made of hyaline cartilage. They're soft, they're flexible, but they are the model from which we will be laying down the calcium in here, and calcium and phosphorus salts and the collagen to make the true bony skeleton. And so about 99% of our skeleton is hyaline cartilage. The other portion of our skeleton is formation is through what's known as intramembranous ossification. So we have endochondral ossification for most of our skeleton, and we have intramembranous ossification for the remainder. And it turns out this is bones that develop from a fibrous membrane. And the bones of the skull, the parietal, the temporal, the frontal, and the occipital, are going to form from intramembranous ossification, as well as the clavicle. I don't know why the clavicle has to be that way, but it is. The beauty of the intramembranous ossification is that our skull has to continue to be able to enlarge to allow for the rapid growth of our brain. And so we have this somewhat flexible membrane that gradually ossifies as our head gets bigger and bigger as our brain grows until it reaches its full size. We have the fontanelle. The fontanelle, the soft spot, is based on those membranes that will eventually ossify, and the soft spot will eventually close. But we have to make sure that we allow for the growth of the brain. And so the skull has membranes instead of cartilage. Okay, so endochondral ossification. It forms bone from a hyaline cartilage model for everything except the four bones of the skull and the clavicles. We use the hyaline cartilage model. The hyaline cartilage functions as a template, and we start converting the hyaline cartilage into bone, usually starting in what's known as an ossification center in the middle of a long bone, and gradually forming spongy bone and then compact bone on top of that. And most of our bone formation is through endochondral ossification. So we form something to start, the process starts, you don't need to remember all these steps here, but we form what's known as a bone collar. It's a ring of bone around the shaft of the cartilage bone. This is a ring of hard bone around the hyaline cartilage bone, the endochondral bone. And we'll start seeing the formation of spongy bone, and then we'll see penetration of blood vessels into this spongy bone, and nerves, and osteogenic cells, and osteoclasts. So we're building right from the start here at about the 6 week mark. And then we start forming secondary ossification centers in the ends of the bones, in the epiphyses. So everything starts growing together. These secondary ossification centers become the epiphyseal plates. Because remember, long bones are going to continue to grow from each end. They're going to grow outward, and they're going to grow lengthwise. This hyaline cartilage model, this hyaline cartilage skeleton, gradually becomes fully ossified except for the growth plates, the epiphyseal growth plates. Those are the remnants of the hyaline cartilage framework, but they stay active till about 23. That's where we get the epiphyseal plate and the epiphyseal line. You know, the dark band I showed you, where growth is still occurring and soft tissue doesn't show on X-ray. And then you saw the one with the white line because it's fully calcified and there's no more long bone growth lengthwise there. And so these are the various steps we see. You can see this is where the bone collar forms right here in the middle of the long bone. And we get a second growth center at each end of the bone in the epiphyses. And that will stay there. The epiphyseal plate will stay there until it closes 23 years later. This is what we look like. 12 weeks. We're about 2 inches long, 3 inches long at this point, maybe 2 inches long, maybe even less. But we can see where the bones have formed. In 6 weeks, we've been really busy because these are bone. These are actual calcium-filled bones now that you're showing up here in this image. The gaps are where the hyaline cartilage remains. The gaps are, they're not real gaps. The cartilage is there, but soft tissue doesn't show up on X-ray. And so we can see the formation of the phalanges and the metacarpals. We can see the ulna and the radius, at least the shaft has formed. Here we see the humerus, or part of the humerus anyway, the tibias and the femurs and the ribs. And we can just see the membranes being converted here, that are becoming the frontal bone, the parietal, occipital, and temporals in here. Clavicle is remarkably almost complete in its shape. So the bone isn't missing. The bone is there. What you're not seeing, what you can't see in this image is the soft tissue version. You can't see the hyaline cartilage version of it. So at about 12 weeks or so, we're maybe 2 inches in length, if that. And we have a pretty good amount of our bone starting to be visible because of ossification. So it didn't take long to start ossifying that soft tissue, ossifying the cartilage, but the process is going to, it won't be finished for another 20 some years. Now, and here we see this is probably about 10 weeks. It's a little less developed than the other image, but here we can definitely see the membranes. Here, the intramembranous ossification takes care of the bones of the skull and the clavicle. Now we can see that this fetus is a little more transparent because the ossification of the hyaline cartilage isn't as far along here because we don't see the bones look smaller. They only appear smaller because we haven't calcified as much of the cartilage. But we can see the membranes very clearly here. The frontal bone, the parietal bone, the occipital bone, the temporal bone, and the clavicle are all going to be laid down for membrane. Okay. And the way this works is very similar to what happens in endochondral ossification. We're not using hyaline cartilage here, we're using membranes, and we start forming bone centers in the middle of the membrane. And the ossification centers develop osteoblasts, which start laying down osteoid matrix, which gets calcified. And we start with spongy bone, and then we end up with the diploid sandwich ultimately. So this is what we see. There's our diploid right there. So anyway, So it's pretty straightforward how we go. We have the two ways of doing it. Endochondral ossification is the majority, the bulk of all of our bone formation. Intramembranous ossification deals with the bones of the skull and, of all things, the clavicle. So once we stop growing, once we stop having longitudinal growth, meaning up and down, vertical growth, if you will, once the epiphyseal plates close, we don't get any newer growth. We don't continue. A normal healthy individual does not continue to grow past 23 years of age. There are conditions that can occur. Don't think it can't happen. It does happen. But the average individual stops growing when the epiphyseal plates close at about 23 years of age. However, we can have what is known as appositional growth from side to side. Our bones will continue to enlarge or shrink from side to side, depending on the stresses placed on them. Bones will shrink and bones will expand as we go through life and the things we do, depending on our activity level. If our activity level is low, then our bone mass is going to shrink. If our activity level is high and we use a lot of energy to do things, then our bone mass is going to be fairly big. So, and this is bone growth is longitudinal. There's our epiphyseal plate. We grow. Until we achieve our complete adult stature. We have this area is going to be functioning. Once that is closed, then we have appositional growth, where we add growth from side to side, because we're always remodeling our bones. It's a constant thing. It never stops until we're dead. And so we hit our adult stature, and then we start remodeling. Now, there are some bones that may continue to grow. Facial bones may continue to grow over time. It's a very slow process, but it does happen. Nasal bone gets bigger, forehead gets bigger, the frontal bone grows, perhaps the mandible grows slowly and gets bigger. This can happen. This is, it's not unusual to see that in older people. And so I've been saying repeatedly, about the epiphyseal plate. Longitudinal bone growth takes place at the epiphyseal plate. Once that closes, we don't get any taller or any larger. The bones can change side to side, because here we have a growth plate at each end of the long bones. We call it the epiphyseal plate, and we see our cartilage cells becoming bone cells. Okay. And when the epiphyseal plate closes, we have the line, and the line indicates, the bright white line on the X-ray indicates that bone growth is over. So if you're examining a skeleton, from a forensic perspective, you can tell a lot by just looking at the bones. Again, if you X-ray the skeleton and discover that the epiphyseal plates aren't closed, then that gives you a pretty good idea of the age of the individual. It doesn't matter how old the skeleton is that you find. It could have been, been around for 100 years, but you can tell the age of the individual within a few years based on whether or not there's an epiphyseal line, or on the X-ray, or there's a dark spot. Because even though the soft tissue is gone, if you find a skeleton that's 100 years old, I don't know why you're going to X-ray it, but maybe you are interested, I don't know, in whatever you're doing. and you discover the dark line there, then it means that they're under 23 years of age. So, okay, now. What controls our bone growth? Well, growth hormone plays a big role here. Growth hormone will, as growth hormone levels increase when we hit puberty, we'll get our rapid proliferation of bone cells and we'll have rapid growth. We call it a growth spurt. Growth hormone gets released gradually from throughout our lifetime from infants to adulthood, at least from there. And growth hormone will continue to stimulate long bone growth, and we gradually get bigger in stature over time. As we go from an infant to 6 years old to 12 years old to 15 years old and then 20 years old. We also have to have lots of thyroid hormone. Thyroid hormone provides the energy that we need for the protein synthesis to take place. Now, when we hit puberty, testosterone in the males and estrogen are going to trigger bone growth, rapid bone growth, and they are going to give us our adult stature. Now, what happens with the female is the amount of estrogen produced by the female causes rapid growth. A female going through puberty will have rapid bone growth and reach her adult stature very quickly. But the high levels of estrogen being produced every month by the female, particularly from the ovaries after they've developed, will cause the epiphyseal plates to close quicker than in the male. Testosterone has a slower response time. Testosterone will stimulate growth spurts, but they don't occur on the same schedule that they do in the female. The male will have his growth spurt a few years following onset of puberty in the female. So males will reach their adult stature later in adolescence, and it takes longer for the growth plate to close. Whereas the female's estrogen, okay, you're going to grow to your adult stature, and then it's going to close, and it's stopped. And so we see that's why we see in the onset of puberty in females, they grow quicker and reach their adult stature earlier than do males. Males are lag by several years, and then they reach their adult stature, and their adult stature may be well, it's already determined by their genetics what their adult stature is going to be. So, okay, now let's. This is a good place to stop. We'll right here in the hormonal effects of bone. We'll come back to this on Tuesday. So, any questions on anything? Okay, then I want to get us out of here. And in lab this afternoon, we're going to be going over the muscles of the body. So if I haven't seen you yet in lab, I'll see you this afternoon. Okay, thanks a lot.